All right, nomenclature. Let's jump right into this. This is the last topic for this chapter, but it's a pretty big topic. It's going to take us a few videos to get through it. What nomenclature is just how we name stuff. That is nomenclature. So really every field, even outside of science, every field of study has nomenclature. It's just the systematic process by which things are named. So we are going to be looking at nomenclature for chemical compounds, and we're going to use what's called the IUPAC system. It's the International Union of Pure and Applied Chemistry, IUPAC. They have a system for naming things that most people use. Really, the only exception to this naming system are a few people that use common names, and we'll discuss those a little bit as we go through these, but most places and most people do use the IUPAC system. It's the most commonly agreed upon way of naming things. So, to start off with here, we are going to learn how to name ionic compounds. So again, ionic compounds are any compound that has a metal and a nonmetal in it. We actually don't care how many of each of these things. If it has a metal and a nonmetal, at least one of each, it is ionic. For the most simple ionic compounds, these are what we call binary ionic compounds. They are binary because they are made up of two things, and two things only. And by those two things, we mean one kind of metal and one kind of nonmetal. You can't actually have more than one of that nonmetal or of that metal. So you can have more than one atom, but as long as it is the same element, it's still considered binary. If you just have two kinds of atoms, we don't care how many total atoms you have. If there's only two kinds of atoms, that is binary. So in naming these types of ionic compounds, we're going to put the name of the metal first, and we're going to leave it alone. So we don't do anything to the metal. We're then going to take the name of the nonmetal and mostly leave it alone, except we're going to take the end of the name and replace it with "ide". So chlorine, as an example here, becomes chloride. So we're going to chop off the end of it and replace it with "ide" instead of "ene". And so this particular molecule then becomes sodium chloride. Because again, we leave the name of the metal alone. Sodium is the metal. So then chlorine becomes chloride, sodium chloride. And this is something I'm sure you've at least heard the name before at some point. This is table salt, is what sodium chloride is. But we can apply the same rules to pretty much anything else. So we have another example here that's already worked out for us. So sodium and fluorine becomes sodium fluoride. Again, fluorine turns into fluoride. We have a few other examples here that I'd like you to give a shot at writing the names for these real quick. So go ahead and pause the video, see if you can work out what the names would be, and then I will tell you what those are on the other side. So go ahead and pause the video now. Alright, so the first one here, calcium and bromine. That will become calcium bromide. Bromine becomes bromide. The next one here, calcium and sulfur, becomes calcium sulfide. And by the way, it's sometimes spelled with an F as well. As far as I'm aware, I think it's just a difference between like American spelling and British spelling. As far as I'm aware, they're both acceptable. I will take either one. But I believe the PH is more correct. I think the PH is actually the British spelling. I prefer the pH personally, but either way is fine. Strontium and phosphorus. Strontium is the metal. Phosphorus becomes phosphide. And that is a little bit different. If you're just replacing the very end of the name, it seems like it should be phosphoride. But I guess at some point someone decided that didn't sound as good, and so they use phosphide instead. So phosphide is the end of that name. And then the last one here, magnesium and nitrogen, is magnesium nitride. So nitrogen becomes nitride. So one thing I want to point out here is that these subscripts have nothing to do with the naming. The only thing that determines the name is what the atoms are, not how many of them there are. Later, that will come into play. But for these very, very simple molecules, because calcium only has one possible charge it can have, bromine only has one possible charge it can have, if you know that you have calcium and bromine, this is the only possible structure. There is no other way for those to come together to make a molecule. And so simply knowing that it's calcium and bromine is enough. We don't need any other information. We don't need to know how many atoms there are. Simply from the fact that it's calcium and bromine, this is the only possible answer. That's not always going to be the case, though, because the transition metals, if you remember our discussion of working out charges using the periodic table, transition metals don't have a nice, easy way of determining what charge they can have. And not only that, many of the transition metals, not all of them, but many of them can have multiple charges. So in one molecule they might have a charge of +2, and in another molecule they might have a charge of +4. It varies depending on the atom. So for the transition metals and any of the other metals that are not in the first two columns or aluminum, we are going to have to represent the charge on the metal with Roman numerals in the middle of the name. So because iron could either be +2 or +3, the iron, just saying iron chloride is not good enough, because that could be either one of these, and these are two different molecules. This one and this one are different. And so because iron chloride is not good enough, we need to specify which iron we have. We're going to put the charge on the metal in Roman numerals in between the name of the iron and the name of the in between the name of the metal and the nonmetal. So in this case here, the iron is +2, which is why you need 2 chlorines to balance out its charge. And so this is iron 2 chloride. Again, the 2 here is not because we have 2 chlorines. That's just a coincidence that those two are the same thing. It's because of the relative sizes of the charges. That 2 is not saying how many of the other thing you have. That 2 is giving the charge on the metal. We'll see examples later where the charge does not match however many of the next ion you have. So this would be iron 3 chloride here. So you have iron that has a +3 charge. Because it has a +3 charge, you need 3 chlorides to balance out the charge. So let's do one of these together, and then I'll have you pause the video and work out the rest. So this first one here, Cu, is copper. O is oxygen. The same naming stuff applies as before. We're still going to chop off the end and replace it with "ide." So oxygen becomes oxide. So then the question becomes, what goes in the middle here? Now we know something is going to go into the middle because copper is a transition metal. or more specifically, because it's not in the first two columns, or aluminum. All the rest of the metals we do need to give the charge for. So how do we determine what the charge is? That's the rub. If copper can have multiple different charges, how do we know what charge this is? The answer is we can look at the other thing. We can look at the other part of the molecule. So in this case, copper is paired up with oxygen, and more specifically, it's paired up with one oxygen. And we know oxygen wants to be -2. So if oxygen is -2, and the molecule as a whole needs to be 0, that means the copper must be +2. And so we're going to put 2 in the parentheses there. 2 in Roman numerals in parentheses. And for those of you that it's been a while for your Roman numerals, 1 is just 1 like that. It's just a single line. That's 2, 3, 4, and 5. We probably won't go above 6. You can. There are situations where you can go above 6, but I don't think we'll ever go above 6. So those are your Roman numerals there. So 1, 2, 3, 4, 5, and 6. For those of you that it's been a while. Okay, so go ahead and try to work out these last 4 here. See if you can come up with the correct name for those. So go ahead and pause the video now. All right, so we have chromium. It's the first metal here. And chlorine, which is going to become chloride, because we have 3 chlorides. Each one of those would be -1. And so that means that the chromium must be 3. Chromium 3 chloride. And by the way, it is not normal to write the charges above the atoms like this. I'm just doing that for your benefit. It would not normally be done. Like it's not a standard thing to do. It's technically actually incorrect to write in the charges like that. I'm just putting them there as a reference for you to keep in mind where we're getting these numbers from. The next one here, Ag is silver. N is nitrogen, which will become nitride. Nitrogen is going to have a charge of -3 because it's in column 15. So if nitrogen is -3, and we have 3 silvers, for the molecule to be neutral, each one of those silvers must be +1. So this will be silver 1 nitride. Next one here, we have cobalt, and then iodide. Iodide is -1, just like chlorine and fluorine. And so this is going to be cobalt 4 iodide. And then the very last one here, iron and oxide, and the charge on this iron is going to be +3. And we know that because each of those oxygens is -2, so that gives us -6 total. We have 2 irons that are going to need to be +6, and so because we have 2, each of them would be +3. So you're splitting up that charge evenly. If the whole of the irons have to be +6, we're going to split that +6 up evenly to give us +3. All right. So the last type of ionic bond or ionic nomenclature we're going to look at here is with polyatomic ions. And even though these molecules are actually technically more complicated because they have more atoms, I actually think that these are the easiest ones to name. because you don't have to worry about changing the endings of the name of the ions or anything like that. It is simply the name of the metal and the name of the ion, and that's it. So these polyatomic ions, they are groups of nonmetals that you normally see staying together. They don't normally separate. Once they're in that polyatomic ion, unless something extraordinary happens, they're going to stay there. They might move around, so the polyatomic ion might get transferred from one molecule to another, but it's going to stay together most of the time. And so they get special names, these groups of nonmetals that stay together as an ion. So in this particular case here, NO2- is nitrite, and it's bonded to sodium, and so this is just sodium nitrite. And that's it. No fancy tricks, no nothing like that, it's just the name of the metal, the name of the nonmetal. We do still have to put in the Roman numerals, by the way, if the metal is not in the first two columns or aluminum, but other than that, it is just the name of the metal and then the name of the polyatomic ion. You do not have to have these polyatomic ions memorized, by the way. You will always have access to some kind of a list of these. It probably won't be this specific list usually, but most of the lists have the same ones on it. There's I don't know, 20 or so common polyatomic ions that you'll see. And so pretty much any list that you come across is going to have those most common ones on it. And so you'll just need to be able to look up those ions and identify them on a table like this. Okay, real quick thing about these polyatomic ions. You might have noticed here on the last slide that almost all of these have oxygen in them, and not just one oxygen. Many of these have multiple oxygens in them. Because of that, these actually get a special name. We call these oxyanions. And it's possible to have a series of these. And what I mean by that is you can have the same number of every other atom in the polyatomic ion and the same charge, but the number of oxygen can be different from one polyatomic ion to the next. So for example, NO3- and NO2-, the only thing that's changing here is the number of oxygens. We still have one nitrogen for each, have a single negative charge with each of them. It's just a different number of oxygens. And so these are what we call the oxyanion series. They can be just 2 ions long like this one, or they can be longer, as we'll see on the next slide here. But for these shorter series, where you just have one ion that has more oxygens and one ion that has fewer oxygens, the ion that has more oxygens always ends in ate, and the one that has fewer oxygens ends in ite. And this is regardless of how many oxygens it has. So notice here, nitrate, the one that has more oxygens, has 3 oxygens. Sulfate, which is the same situation, it has 4 oxygens though. So we had 3 oxygens over here, 4 oxygens over here. We do not care the total number of oxygens. All we care about is which one has more, which one has less. So because the sulfite has fewer, it gets the ite ending here, and the sulfate has the ate ending because we have 4 and 3. So the number is not important. What's important is the relative number of oxygens. So the one that has more oxygens ends in ate, fewer oxygens ends in ite. For the longer series, like the chlorine series, where there's more than just 2, we still keep the ate and the ite. So ate indicates that you have more oxygens, ite represents that you have fewer oxygens, but we're going to add on a prefix so that the one with the absolute highest number of oxygens is now per, and since this is chlorine, it will be per chlorate, and the one with the absolute least number is hypochlorite. So we still keep the ate and the ite, but because we have more ions in these longer series, we're going to add on the prefix of per and hypo. So again, perchlorate is the maximum number, chlorate is one fewer, chlorite is one fewer, and hypochlorite is the fewest. It's the smallest number of oxygens in the series. All right, so we have just a couple examples here of naming a few of these. So why don't you go ahead and work through both of these slides here. So this one, you're given a formula and asked to give the name up above and then the opposite on these three. And then on the next slide here, it's pretty much the same thing. You're given the name and asked for the formula. It's going to be a little bit more complicated though for some of these. So like here we have the Roman numerals popping in again. Take a look at those, see if you can work out the names and formula, and we will work through it again together here in just a second. So go ahead and pause the video and work through those. All right, so the very first one here is worked out for us. We have sodium, and then we have carbonate. So CO3 2 minus is what you would be looking for on the table back here. So let's see, where is that? There it is. Carbonate. And so we have sodium, we have carbonate, so the name is just sodium carbonate. Same thing here. We have potassium, which is K, and then PO4 is phosphate. And again, you can just find that on the table back there. PO4 is phosphate, which has a -3 charge, which will balance out the +3 charge from those three potassiums. Next here we have barium and nitrate. Notice that we don't care that there's two nitrates there. Doesn't matter. It's just barium and nitrate. Again, we don't have to put the Roman numerals in for barium because it is in the second column. So it is only ever +2, which by the way is why we needed two of those nitrates, because nitrate only has a charge of -1. So we got -1 from each of those to balance out the +2 from the barium. Potassium permanganate is next. Permanganate, I think I'm spelling that right. Spelling is not my strong suit. The next one here is a little bit tricky because now we don't have any metal. But if you remember from, I believe, the last video, we talked about how, very briefly, how there was one exception to metals always being the cation, and that was when you had ammonium, NH4+. So this is the only time where we'll have a cation that is not a metal, is if we have ammonium. So we're just going to have ammonium sulfite. That's what that is. And actually, I think there's a typo there. That actually should be there should be 2 ammoniums. But regardless, you're going to spell it the same way. You're going to name it the same way. It's ammonium sulfite. Okay, lithium chromate is the name that's given to us. So we know we have lithium. We know that we have chromate. If we go back and look at our list here, chromate has a -2 charge. So if this is a -2 charge, lithium has a +1, we need 2 lithiums to balance out the charges. Because again, we still have to get the charges balanced. We can't just stick lithium and chromate in there and call it good. We have to make sure that the charges are balanced. So the next one here, strontium. Perchlorate has 4 oxygens and a -1 charge. Strontium is in the second column, so it's going to be +2. So we need 2 perchlorates. So we have +2 from the strontium, -2 from both of those perchlorates. Put together would be -2. So the last one on this slide sodium, and phosphate. Phosphate has a -3 charge. And so to balance out that -3 charge, we need 3 sodiums, because each of those have a +1 charge. Alright, last few ones here for this video. Sodium perchlorate, which is very similar to the one we had back here, strontium perchlorate. Only now, perchlorate, -1 charge, sodium, +1 charge. That's all we need. It's not normal, by the way, to put parentheses around this. I don't think it's technically wrong to put parentheses around that. I certainly wouldn't count it as wrong, but they're not needed. If you have just one perchlorate, you don't need to put parentheses around it. Strontium nitrate. Nitrate, if you go back and look at the table, has a -1 charge. Strontium is +2. So we need 2 nitrates to get those charges to balance out. Iron 3 bromide. We have iron. We have bromide. And this is bromide, not bromate. So back here, let's see, where's bromate? Well, looks like it's not on this list, but it was over here, so there's bromate. That is not the same as bromide. Remember, bromide, the IDE, indicates that it is a single kind of atom. It's just one atom, one element that's present. Bromate tells you that you have a polyatomic ion. So this is going to be FeBr3. Because the 3 here tells you that the iron has a +3 charge. Bromines each have -1, or bromides, I should say, each have -1, and so it's going to take 3 of those to get a balanced chemical. Similarly here, tin 4 oxide. We have tin, we have oxide. The oxygens are -2 for each one. The tin, we're told, is +4. And so it's going to take 2 of those oxygens to give us a balanced formula. So then the last one here, ammonium. Sulfide, again, the IDE tells us that it is just sulfur, nothing else. Ammonium has a +1 charge. Sulfide has a -2. And so we are going to need 2 ammoniums to get a balanced chemical. Because if we have -2 here, we're going to need 2 of those. Alright, so it's a little bit of a longer video here, but the naming of ionic compounds is the biggest group that we're going to look at. So the next couple videos should be shorter for the other 2 kinds of naming. But we'll pick up next time with hydrated compounds, which are a very brief side note for the ionic compounds. So we'll pick up there next time.